Hello, this is Professor Shannon Gracie back with you in our Intermediate Algebra course. Today we will be covering Section 8.3 from Blitzer's Introductory and Intermediate Algebra for college students. This section covers the algebra of functions, so we'll continue with our exploration of domain, and we'll use the algebra of functions to combine functions and determine the combined domains. So here we go. Warming it up. Why don't you guys go ahead and do A, B, and C, and we'll be evaluating each of these functions at the given input values. Right? So pause the movie and then check your work when you're done. Good luck. Okay, let's see how you did. So the function is the square root at x. So we'll be evaluating the square root at 4, which has a result of 2, since 2 squared is 4. And remember, what we're doing is every time we see an x in part A, we're going to plug in a 4. In part B, we'll be plugging in a 0. And in part C, we'll be plugging in 196. So the square root of 0 is equal to 0. And the square root, actually, the function evaluated at, this is equivalent to the square root of 196, which has a result of, 14, because 14 squared is 196. And this is what we plugged in for each one. And one other thing I wanted you to realize, if you were evaluating these function values for the purpose of graphing the function, these would be your x values, and the end result would be your y values that correspond. So you'd have the ordered pair 4, 2, 0, 0, and 196, 14. Okay. So, moving right along, finding a function's domain. If a function f does not model data or verbal conditions, its domain is the largest set of real numbers for which the value of f at x is a real number. Exclude from a function's domain real numbers that cause division by 0 and real numbers that result in a square root of a negative number. Okay, so let's find the domain of each of the following functions. So in this case, we have a square root in part A. So what we want to say is that the radicand, which is the expression, algebraic expression inside the square root, is greater than or equal to 0. So if we add 1 to both sides, we will get x has to be greater than or equal to 1. And the way we do that, we write that, remember, in interval notation is one to infinity. Okay. All right, so for part B, what do we want to make sure of? Is it okay for that to be a negative? Yeah, it is. But we do not want the quantity in the denominator to be equal to, good, 0. So 1 minus x squared, we just don't want that to be equal to 0. So recall that this is a difference of squares, so we can factor. So we don't want 1 plus x to be 0. We don't want 1 minus x to be 0. So that gives us that x should not be equal to negative 1, or x should not be equal to 1. Now, in interval notation, if you haven't learned this already, we basically are saying every number except for negative 1 or 1. So we can go all the way minus infinity to negative 1. We put parentheses around the negative 1 because we don't want to include it. Or, now or is denoted by this union sign. So we don't want negative 1, but all the numbers in between negative 1 and 1 are okay. We don't want to include 1 because that was another one of our conditions. So our last part of the interval is going to go from 1 to infinity. So these are all the numbers we can include, and we put parentheses around the negative 1 and the 1 because we do not want to include those numbers because they'd yield a 0 in the denominator. Okay? So the last one, what kind of graph is that? Good, it's a line. And a line, there's no way that it has a denominator that can be 0. There's no restrictions on that. So any real number can be plugged into that, and you'll be able to evaluate the function and get a result. Okay? All right. So the algebra of functions. We're going to take a look at these functions, and we'll graph a couple of these situations by hand, but some of the graphs are a little above your pay grade. So we'll be using, I'll illustrate those using a graphing calculator, and then you can just reproduce the graph on your grid as best you can. So here we go. F of x is equal to negative x, and g of x is equal to 3x minus 5. So we'll just have a regular scale. This is going to be the x-axis. And I'm just going to call this one the y-axis because we've got two different names for our functions, so I don't want you to get confused about that. So here we go. F at x, actually I'll do this in green. We'll graph this one in green and the other in red. F of x equal to negative x. The slope is equal to negative 1. And the y-intercept is at the origin, 0, 0. If you need a review on this, you could go to my Chapter 3 lectures. That would be on mathchick.net. You can scroll down to the introductory algebra page. All the movies are listed there. So here we'll be at 0, 0 for our intercept. Down 1 to the right 1 is negative 1. You could go up 1 to the left 1. That's also a slope of negative 1. So this guy has a graph that looks like this. Oops. the phone. Okay, and our second graph we'll do in the red. This is g of x is equal to 3x minus 5. In this case, the slope is 3. The y-intercept is 0, negative 5. Okay. So graphing 0, negative 5, we have 1, 2, 3, 4, 5. And then the slope of 3, 3 up, 1 to the right. I'll do another point so I can get the shape of my line. It'll look something like that. Okay, so we've got two of these functions graphed on the same coordinate plane, right? Now, if we were to look at the sum of these functions, you could literally look at the ordered pairs, right? If you take a look at, for example, each function evaluated at 0, and if you added the y values, if you look here, the green graph has an output of 0. The red graph has an output of negative 5. So if we were to add these two functions, we would end up getting an ordered pair at 0, negative 5. Right? Now, let me go ahead and label the graph. You've got one line being added to another line. So your end result is going to be linear. And you'll see in a moment when we add the two lines. But let's get another ordered pair so we can finish our picture. Do you see here at an input of 1, right? We have 1, negative 2 for the red line, okay? And that function was g. And then we have 1, negative 1 for the green line, and that function was f. So negative 1 minus 2 gives us a result of negative 3. So at negative 1, we're going to be down at 1, 2, 3, negative 3. And if you want to look at another one, again, it's the green graph plus the red graph. Let's see what we've got at 2. The green graph is at negative 2. The red graph is at positive 1. So negative 2 plus 1 is negative 1. So we'd have an ordered pair at 2, negative 1. And do you see that we have this constant slope? 2 up, 1 to the right. 2 up, 1 to the right. So when we add these two functions, we'll get another line looking something like that. So now let's take a look at it. Well, f of x, what we were doing is adding f of x plus g of x. F at x was negative x. G at x was the one that was 3x minus 5. So again, we had done this one in green, and we had done this guy in red. So if we add these guys, you see that negative x plus 3x is 2x's minus 5. And if you check it out, that's a line with a y-intercept at 0, negative 5 and a slope of 2. And that's exactly what our picture is. Pretty groovy, huh? All right. So that is the result for that one. Now, similarly, we could do the same thing, looking at the difference of functions, Or we can go ahead and directly, evaluate it like this. So f at x minus g at x. So again, we'll just call this x. Actually here, since we combined them and only had one graph on the graph from before, why don't we go ahead and label this guy f plus g at x. This one will be f minus g at x. We'll do the regular scale. So remember that f at x was negative x, and then minus the quantity 3x minus 5. And this is what f minus g at x will be. From above, this was our green graph, and this was our red graph. So f minus g at x will be negative x minus 3x plus 5 when I distribute the minus through. So the end result for f minus g at x will be negative 4x's plus 5. So if we graph that using slope-intercept form, we have 0, 5 is the y-intercept. And then we have a slope of negative 4, so we can go 1, 2, 3, 4 down and 1 to the right. Do one more. And our line will look something like this. So this is what it looks like in function form, and that's the picture. Now, let's go back and let's talk about domains. Okay, so here the domain of the green graph, do you see, is all real numbers. The domain of the red graph is all real numbers because they're both linear functions. And if you come here, what happened? We got another linear function when we added and when we subtracted on the next one. So do you see the domain is going to be all real numbers? Good. And what about the range? Good. It goes down infinitely and up infinitely. So the range is also all real numbers. And we get the same, result for the difference. The domain is all real numbers, which, as you notice, is the overlap of the domains from the original. And the range itself is all real numbers. All right, so the product. So for this one ends up being it's going to end up being quadratic in form. So we'll go ahead and we'll work it out, and then I'll show you how you could graph it on a graphing calculator. We're not using graphing calculators in this class, but for if you go on to pre-calculus, then you might be using them. So here we go. Fg at x will be, so f at x was negative x. We're multiplying that to 3x minus 5. Oops. So we will get negative 3x squared plus 5x's. So this one has a degree of, 2. So therefore, we end up with something that's quadratic in form. So now I'm going to go ahead and pull up just an old TI-83 emulator. And we'll go to our y equals. And this is how we'd enter them enter this in, we use the negative sign, and that's 3 times x squared plus 5 times x. And we want to graph that. And this is the picture that we get, right, of this. This is the picture that we get. And by the way, the scale is, let's take a look. I'm going to go zoom standard, which will make it 10 up, 10 down on both axes, and then that way we can take a look at the picture. And as I said, you just copy this the best you can. Okay, so again, I don't like how that's looking there. Move it down a little. Cover up the grid. Good. Okay, so this is 10. This is x-axis. This is FG at x-axis. This has a scale from -10 to 10 on both axes. So that's the picture of this graph. And so notice this time we were multiplying them together and we got a parabola. Right? Again, our domain is the overlap of the two domains, right? Which is -infinity to infinity. And the range, if you take a look at the range, it ends up being a little bit over 2. If you look at if you figure it out exactly, which we're going to learn how to do later, that ends up being 25/12. So basically, it's got negative values going all the way up to 25, positive 25/12, and that is included. And we're going to learn in later sections how exactly we can get the maximum of a quadratic. All right, so here we go. Last up will be the quotient. Again, we're going to do this guy on the graphing calculator. This ends up being f at x divided by g at x. So f over g at x is -x is f, and 3x minus 5 is g. Nothing we can really do to simplify that one. So this is the end result. Now, what is the domain for this guy? We now have a denominator, right? So 3x minus 5, what condition do we place on that? Good, that it's not equal to 0. So 3x not equal to 5, x not equal to 5/3. So the domain for this guy is going to be -infinity to 5/3. And then remember, or is that union symbol. And we would go 5/3 to infinity. Everything else is okay, just not the 5/3. All right, so let's look at a picture of it. So now we'll have -x divided by, you got to put parentheses around the denominator, so that'll be 3 times x minus 5. And we get kind of an interesting looking graph there. Let's zoom in on this one. So when you see a line like that, that means you have something called a vertical asymptote. Vertical asymptote. So here, let's see what our window is here. It looks like x is going to negative 2.5 to 2.5, and as is y. So I'll copy this. There we go. All right, so again, we've got x and we've got our f divided by g at x. And each of those is going to 2.5, negative 2.5, negative 2.5, 2.5. So it looks like our range, this is another thing about the graphing calculator, okay? When it goes on, it doesn't write in arrows. You have to recognize that the graphing calculator just can't make arrows, and you've got to understand that. So here the range is looks like it's going from minus infinity to infinity. It looks like it's got it's got a horizontal asymptote. Actually, there'd be, let's leave the range for now. We're just gonna, I don't want to get too complicated and confuse you about stuff you're going to understand later. We'll just stick with the domain here, which actually I think I asked for. Nope, I didn't ask for that. But you got it. It was a bonus. Okay, so here are the official definitions that we sort of explored. Okay, so f and g are two functions. The sum, f plus g, the difference, f minus g. The product, f times g. And the quotient, f divided by g, are functions. Whose domains are the set of all real numbers common. So overlapping domains of f and g, defined as follows. So the sum, as we learned, f plus g at x is equal to f at x plus g at x. F minus g at x is equal to f at x minus g at x. F times g at x is equal to f at x times g at x. And the quotient, f over g, or f divided by g at x, is equal to f at x divided by g at x, provided that g at x is not equal to 0. Okay? So let's go ahead and find these values, given that f is x squared plus 4x and g is 2 minus x. So find the following. So why don't you guys pause the movie and see if you can do these on your own. All right? Good luck. All right, my friends, let's see how you did. This is equivalent to f at x plus g at x. Well, f at x was x squared plus 4x's. And g at x was 2 minus x. So, go ahead and have So F is the blue. And G is the yellow. Alrighty. So we have F plus G at x is equal to x squared plus 3x's plus 2 when I combine like terms. Now, the cool thing is, once I've done that, right, notice that it's asking us to find f plus g at 4. So instead of finding, f at 4 and then g at 4, and then adding the results, we can use the function that we made. So do you see that this is 4 squared, I'm using the result from above, plus 3 times 4 plus 2. So f plus g at 4 will be 16 plus 12 is 28, plus 2 is 30. And we're done. And if you opted to do it the other way, you would have gotten the same result. Now, notice that this one's being a little tricky. Instead of writing it as f plus g at -3, it's writing it in that second format like this one. Do you see that that's the same as this, right? So I'm going to go ahead and say, use my function I found before. This is going to be -3, the quantity squared, plus 3 times -3, plus 2. So remember, f at -3 plus g at -3 will be, we'll have 9 minus 9 is 0, plus 2 is 2. So at the end of the day, we get a result of 2. Okay, so let's move on to finding the product. This product will be f at x times g at x. So fg at x will be x squared plus 4x's times 2 minus x. So don't forget to use that distributive law twice. This was our g, and this here was our f, and we're multiplying them now. So fg at x will be, so we'll have x squared times 2 is 2x squared. X squared times minus x is minus x cubed. 4x times 2 is plus 8x. And 4x times negative x is going to be minus 4x squared. So when we put them in descending order and combine like terms, we will get negative x cubed minus 2x squared plus 8x's. Now again, I can use this function that I just made to evaluate the product at 3. So we will have the opposite of 3 cubed, right? Minus 2 times 3 squared plus 8 times 3. So fg at 3 will be negative 27. 9 times 2 is 18, so minus 18 plus 24, which gives us a result of negative 21. Okay, so now, what is the domain of f over g at x going to be? So here, you see this will be f at x over g at x. So f over g at x will be f of x was x squared plus 4x, and g of x was 2 minus x. So we don't want 2 minus x to be good, 0. So that means that x should not be equal to 2, because 2 minus 2 is 0. So the domain will be minus infinity to 2, remember parentheses, union, to infinity. And we are all set. We just finished 8.3. One more section left to go in Chapter 8, and then we'll be done with Chapter 8. So do your homework for the problem set for 8.3 as soon after the lecture as you can, and have a fabulous day.